In this video, we'll introduce regression models, simple regression model, and multiple regression model. We'll also generate household income and consumption data using Mathematica software.
Let's assume variable y is function of a variable x. In symbolic form, we represent y as function of x.
Or, in another case, variable y is function of more than one variable, x1, x2, x3, and so on.
In symbolic form, we represent y as function of more than one x.
Regression in the first case is called the simple regression model, while that in the second case is the multiple regression model. Earlier, we saw the general functional forms of the two. Now, the specific forms in equation form are. Here we see simple regression model both in functional form as well as in specific form or parametric form, equation form if you will. Parameter alpha is intercept. And beta is slope.
This is multiple regression model shown here both in functional and specific form. Notice here the slope parameters are more than one. Beta 1 shows the rate of change in y because of a unit change in variable x1, with the condition that as if all other variables are constant. Likewise, beta 2 shows the rate of change in y because of a unit change in variable x2, with the condition that as if all other variables are constant. Similarly, beta 3 shows the rate of change in y because of a unit change in variable x3, with the condition that as if all other variables are constant. Note that parameter alpha is intercept and, conventionally, it can also be shown as beta 0 or beta naught. It measures in a dynamic system a change in variable y in a condition that there is no change at all in any x variables.
Next, let's look at an example of a simple regression model in case of household consumption. Here, the general functional form says that the consumption of a household is a function of its income. The specific equation form says that consumption of a household is determined by intercept parameter alpha plus slope parameter times the level of its income. Slope beta here measures what is called as marginal propensity to consume, or MPC, which is the fraction of income to be consumed. Rest of the income is saved or invested in business, but not consumed in consumer market.
We need data to analyze consumption function of households. Monthly consumption is related to monthly income. In this age of information, economies which maintain their economic data, we can easily find that data available on the web. However, for what are called as Monte Carlo studies, or simulations, we can use statistical softwares to generate hypothetical data to study regression models. One of such softwares is Mathematica, which we'll use now. There are many other softwares of such kind which we'll use in other videos, such as eViews, Microsoft Excel, Stata, RPackage, and Python, and many more.
Let's start Mathematica. Here, we're in Mathematica environment. Okay. As far as the income of a household is concerned, we assume a range of monthly and therefore also yearly incomes. The minimum we assume is $400, whereas the maximum limit is $6,500 per month. Multiplying with 12 gives minimum yearly income of $4,800 and maximum yearly income is $78,000 for our sample of households. Further, we classify households into three groups depending upon their income levels and their probable consumption behaviors. First group is less well-to-do, or poor, if you will. Their income range from $400 to $800 per month. Next is the middle-class households. Their income range from $800 to $5,000 per month. The third class of households are relatively well-to-do, or rich, if you will. Their income range from $5,000 to $6,500 per month. As the code is written here, if we hit return on the keyboard, we'll get the range of the incomes in the three groups. So, the difference between maximum and minimum incomes in three groups is $400, $4,200, and $1,500, respectively.
Next comes the concept of consumer behavior, that is marginal propensity to consume, also to save, which determines expenditure behavior of households. MPC is the fraction or percentage of income that a household is willing to spend. The remaining fraction is called MPS, which determines the saving portion of household income. The saving can become an investment when a household acts like a business or an entrepreneur. We assume the first group with low incomes spends a major portion of its income, 95 to 100%. Middle income group spends 80 to 95%. And relatively rich people spend 60 to 80% of their income, saving the remaining. Note the way we defined these MPCs in Mathematica. They are random real numbers in their relevant ranges. This way, we'll generate unique specific MPC for each of our household in the sample. 1 minus MPC is the MPS. Note that every time we hit return on the keyboard for this Mathematica code, we generate new set of MPCs and MPSs for each household in the sample.
The symbol N shows that we're planning to work with 50,000 households in our sample. Look, here we define a set, or a list, also called a row vector. It contains three income ranges for the three household groups in our generated sample. Let me ask you, out of the 50,000 households, how many we should place in each group? Here we assume that 60% households belong to the middle class, 20% each to the poor and the rich classes. So, 30,000 households belong to the middle class and 10,000 each to poor and rich classes.
Let's generate our data for income of 50,000 households. We use random integer function for each of the three income groups. Mathematica generates random integer within the two limits given to it. We use this function 50,000 times. $10,000 times for the first group, 30,000 times for the middle class group and 10,000 times for the third group. These random integers are generated within the minimum and maximum incomes defined earlier. This income list is list of three lists. One for each group of households. Therefore, at first, Mathematica shows the length of vector as 3, telling that there are 3 elements in the vector, that is, 3 lists for 3 groups. The income list actually contains 50,000 income elements. To make Mathematica to show them in one go, we use the Mathematica function called flatten. It flattens the 3 lists, merging 10,000, 30,000, and 10,000 elements, respectively, for 3 groups of households.
Next, let's confirm and have a look at 10 income observations from each of 3 groups. Here, this first table list gives us 10 observations of first income group. Observe that all of them are in required income limits. All of them are between $400 and $800. Notice, for the next code, we are telling Mathematica to start fetching observations from 10,000 plus 1 and end at 10,000 plus 10. Again, these incomes are within the required limits, $800 and $5,000. Finally, for the third group, we have the 10 observations within limits, $5,000 and $6,500.
Here, in this piece of programming code, we're telling Mathematica to fetch 10 observations each from all 3 groups simultaneously, and also show limits of income. This gives us 10 observations each for 3 income groups on a single screen. We see and compare at a glance. Also note the programming code is such that every time we hit the return on keyboard, we get a new set of household income observations.
Here we generate a unique MPC for every single 50,000 households. While generating these MPCs, we also make sure that they are generated in such a way so that it falls within the limits according to the 3 groups of households defined earlier. Notice this Mathematica function shown by colon and equal sign, dot over dot and equal sign, if you will. It is a special type of assignment or equal function. Every time we use what is on the left-hand side of it, Mathematica actually runs what is on the right-hand side of this equality assignment symbol. We define three such functions: Random MPC Group 1, Random MPC Group 2, and Random MPC Group 3. So, every time we use the function, for example, Random MPC Group 1, we get a unique MPC for a household included in Group 1 of our 50,000 households. Mathematica makes sure that the MPC satisfies the numerical interval imposed on the household from Group 1. This set of programming code makes sure that similar type of MPCs are generated for Group 2 and Group 3 also.
Here, we generate consumption expenditures of 50,000 households. Expenditures are generated for three groups of households with different income levels. Income and MPCs are randomly selected and multiplied for three groups. Notice the range variable I. It ranges first from 1 to 10,000, then from 10,000 plus 1 to 40,000, and then from 40,000 plus 1 to 50,000. To merge the three lists, we have used the flatten function of Mathematica. Because we have already used a flatten function, when we check the length of the consumption list, it tells us that the list contains 50,000 elements. So, the three groups are already merged in consumption row vector.
In the next three tables, we check 10 first pairs of observations of income and its corresponding consumption for three different groups of households. For the first group, the first observation tells us that household has monthly income of $734, out of which $705 is the monthly consumption expenditure. Sixth observation shows that monthly income is $400, out of which $393 is the monthly consumption expenditure. Note that to observe first 10 observations for the second group, we instruct Mathematica to pick observations from 10,000 plus 1 to 10,000 plus 10. First household in this group has monthly income of $2,024 and spends $1,711 as consumer expenditure. Sixth household in this middle-class household earns $2,672 monthly income and spends $2,149 on consumption. To have glance at 10 observations from third group, which is relatively rich households, we instruct Mathematica to pick observations from 40,000 plus 1 to 40,000 plus 10. First household in this group earns $6,496 monthly and spends $4,286, saving the rest. Eighth household in this group earns $5,875 and spends $3,981, saving the remaining. The last point to emphasize is that the way we programmed Mathematica, both income and consumption functions are dynamic random functions. Every time we hit them on our keyboard, they generate new 50,000 income and consumption observations for households.
Here we look at 50,000 income observations simultaneously. As it is a very large group of observations, Mathematica first confirms that do you want to expand all the 50,000 observations? When we select Show All, it expands the table, showing all 50,000 income observations. If we hit the cell again, all 50,000 observations are recalculated, giving new set of data. Here we look at 50,000 observations of consumption all together. We have flattened the list of 3 lists and opted for Show All option again. And now the last cell of this Mathematica notebook. Here we'll look at 100,000 observations simultaneously, income and consumption side by side.
In the follow-up video, we'll use the household data generated here to estimate intercept alpha and slope parameter beta using ordinary least squares method.